Hello and a very good day to everyone. My name is Wan Ahmad Safwan bin Wan Asmawi and I am from Group 12. We'll be present to you about our final projects of finite element methods. So we will do the beam analysis using an Abaqus programs. So before we start our presentations, I would like to introduce to you our group members. The first one is Daniel Azrael Gok. The second one is Muhammad Adam Abbas. And the third one is me, Wan Ahmad Safwan. And the last one is Yoga Farhans Muhammad Yohendri.
So, what is a beam? A beam is a structural element that capable to withstand load primarily by resisting bending. Beams are used to support weight. In these projects, our group will analyze the finite element modelings to find the maximum deflections and the maximum stress of the beams. And we will determine the best methods in order to do these finite element modelings. Next, there are variety types of the beams.
So in this project, we will only be using the cantilever beams, which is a fixed support beam. And we will also only analyzing the symmetrical I-beams, unsymmetrical I-beams, and also the L-angle beam.
My name is Muhammad Adam Abbas and I will be presenting the objectives of question 1 and also the sample of calculations. The first objective of this question was to determine the maximum deflection and maximum stress of the beam using 1D modeling, 2D modeling, and also 3D modeling. Secondly, to discuss and compare the accuracy for each modeling. Lastly, to determine what would be the best method for beam modeling. As you can see in the figure shown, we were given a distributed load P of 80 Newton per millimeter and also a length of beam L equals to 1,100 millimeters. Next, we discuss the problem modeling of this question. In modeling this question, we set a uniformly distributed load of 80 Newton per millimeter and we set at the very left end of the beam as fixed supported. At this point, the moments and forces are equal to 0 and these boundary conditions can be used in the sample of calculation later on. This figure shows the model that was set up by using 2D modeling where we determined the weight, whereas this figure illustrates the model that was set up by using 3D modeling where we sketched the I-beam and extruded it in 3D. Next, we head to the calculations. Firstly, we calculate the values of load, moment of inertia, total cross-section area, and also Ky. After calculating these values, from this figure, we calculate the moment about z-axis, obtaining equation 1. Also, we generate the equation of shear force, which is shown in equation 2. Since we know the general equation for deflection by bending moment is given by equation 3, now, by simply substituting equation 1 into equation 3, we obtain this equation. By integrating this equation 2 times, we obtain this equation where we have C1 and also C2. Next, by applying boundary conditions at fixed support, C1 equals to C2 equals to 0, and the maximum deflection occurs at x equals to L. Next, by substituting L into the x values, we get equation 4. Then, we substitute the values of P, L, E, and I that were calculated earlier into equation 4, and we obtain the maximum deflection of the beam due to bending moment, which is given by 27.5932 millimeters. Now, we know that the general equation for deflection due to shear force is given by equation 5. By substituting equation 2, the equation of shear force obtained just now, into equation 5, we obtain equation 6 consisting of C3. Again, by applying the boundary conditions at fixed support where C3 equals to 0 and the maximum deflection occurs at x equals to L, we obtain equation 7. By substituting the values of Ky, G, and S calculated earlier, we obtain the maximum deflection of the beam due to shear force, which is given by 1.5731 millimeters. Finally, we calculated the maximum displacement of the beam, which is the summation of maximum deflection due to bending moment plus the maximum deflection due to shear force, and we obtain a value of 29.166 millimeters.
So next, we have the results for the 1D modelings. Here we provide you an animations of the deformations of the beam. So at the end of the beam, we can determine the maximum displacements, which the value is 2.87 times to the power of 10 millimeter, and the fixed support here, we have a value of displacement of 0. Next, for the stress for 1D modeling. Now we can determine the maximum stress did not occur at the end of the beam, but it occurred at the fixed support of the beam. As for 2D modeling, the displacement animations we provide here, we can see it same as the 1D beams, where at the fixed support, the displacement value is T0, and at the end of the beams, we have the maximum displacement with the value of 2.893 times to the power of 10. Next is the maximum stress for 2D modeling. As for 2D modeling here, we can see that the stress maximum occur at the bottom of the fixed supports. As for 1D modeling, it's only a line, so we cannot determine at where did the maximum stress occurs. So as for 2D modeling, we can know the stress occurs at the bottom of the beam. Next, for 3D modeling, here is the animation of the deformation. It's still the same. We have the highest displacement at the end of the beam, and the displacement at the fixed support is T0. This is because we have set a boundary condition for 1D, 2D, and 3D modeling, the moment equal to 0 at the fixed support. Next, as for the stress, we can see here the red arrow is the maximum stress for the beam with the value of 9.168 Pascal. And we know as we are analyzing an symmetrical I-beam, so an I-beam here at the middle is the web and the flat surface here is the flange. So the maximum occur at the flange and at the bottom of the fixed support. Here is the displacement table and the graph of the beam. As we can see, we plotted the displacement and it's almost the same. So to determine the best method, we have calculate the errors, and we can 3D has the lowest error with the value of 0.082%. Thus, we can say the best method of modeling is 3D method modeling for finite element analysis of a beam.
Hello, my name is Dina Azrilgo and I will present the question 2. The objective of question is to develop finite element modeling to find the maximum deformation of the beams, to compare and discuss the results with symmetrical I-beam, which shapes of beam would you recommend being used in any general structural design. So these are the problem modeling that we have done using the proper coordinates. So using Abaqus software, we managed to create this cross-section for each case. We have case 2A, case 2B, and case 2C. So these are the properties of the beams. We have the coordinates, elastic modulus, elastic shear modulus, Poisson's ratio, material, surface area, centroid, length of beam, pressure, second moment of area, surface of web, surface of flange, and total surface. And then we have the boundary conditions. We have the L-shaped beam, unsymmetrical I-shaped beam, and the symmetrical I-shaped beam and the unsymmetrical I-shaped beam. So the beam has a fixed end at the left side. So these are the calculation for the applied load and pressure. We have the formula P equal to F over L, which F is the force and P is the pressure. For case 1 pressure, we have the P equal to 80 times 1100 or 1100 times 50 equal to 1.6 Newton meter squared. Using the same method, we have 2 Newton per millimeter squared for case 2. And for case 3, we have 1.33 Newton per millimeter squared. So these are the Abaqus result. As you can see, for the U2, have the maximum deformation of 8.586 times 10 to the power of 1 millimeter squared. And then for the unsymmetrical I-beam, we have the 2.423 times 10 to the power of 1 millimeter. And for the unsymmetrical I-shaped beam, case 3, we have the maximum deformation of 2.773 to the power of 10 to the power of 1 millimeter. So these are the results that we can see, and the difference between the three cases and the first symmetrical I-beam shape. And these are the graph that we have done displacement against length of beam. As we can see that the asymmetry L-beam has the highest deformation.
Using the best method that is used in question 1, which is 3D modeling, we obtain sets of beam deformation analysis of 3 different beams: L-shaped beam, unsymmetrical I-beam 2B, and another unsymmetrical I-beam 2C. Comparing maximum deformation of symmetrical I-beam in question 1 and L-shaped beam in question 2, we can observe from obtained data that with the same distributed load applied of 80 Newton per millimeter and with the same length of 1100 millimeter, maximum deformation of both beams are different. This is due to shapes of the beam. At 1100 millimeter, or at the end of symmetrical I-beam, maximum deformation of I-beam in question 1 is equal to 28.7 millimeter. On the other hand, deformation of L-shaped beam on the same point is equal to 85.86 millimeter. In the case of unsymmetrical I-beam 2B, the maximum deformation is at 24.23 millimeter. And lastly, displacement in unsymmetrical I-beam 2C is equal to 27.73 millimeter. From all obtained maximum deformations data, the largest value of maximum deformation is in the end of the beam is on L-shaped beam, and the smallest value of maximum deformation is on unsymmetrical I-beam 2B. As a result, we can conclude that unsymmetrical I-beam 2B has the smallest maximum deformation of 24.23 millimeter on the end of the beam, when beam is applied with 80 Newton per millimeter distributed load on top of the beam. To conclude, the objective of this project is to determine the best method to find the beam deflection with finite element modeling analysis is achieved, which is confirmed that the best method is 3D modeling analysis. The reason why we believe 3D modeling is the best method is because of it gives the least percentage of error compared to the analytical calculations. Other than that, it is due to each member inside the model is divided into multiple parts of a certain shape. The mesh size of the model affects the final results also. From this project, it can be seen that the shape of the cross-section of the beam does affect the deflection. The beam with unsymmetrical shape like case 1, question 2, the L beam, gives a very large deflection compared to the other cases, whereas the I beam in question 2 gives way smaller deflection than the L beam. With all the results obtained, the shape of beam that is most recommended for structural design is case 2 unsymmetrical I beam that has smaller flange on top and smaller flange on the bottom. Thank you.